Chapter 5, Section 3, Adept, factoring trinomials with GCF, meaning with a greatest common factor. So look at this trinomial. I have 2x squared minus 10x plus 12. This is slightly different than the previous video because the coefficient, meaning the number in front of the x squared, it's not 1 this time, right? So when that happens, we can't quite factor it as we did before. Well, we should always look for a GCF first, regardless of what type of factoring we're doing. Well, it turns out that that's 2. I can divide 2 out of everything. So that would leave x squared minus 5x plus 6. Okay, so that factoring is done. But look here now. That remaining trinomial, that looks an awful lot like the types of trinomials that we saw in the previous video, which a lot of times are factorable. Well, this 2 is still here. The x is there. Now, in order to factor these, we want to find two numbers such that they multiply to positive 6 but add to negative 5. All right, well, what numbers could work? Well, 3 and 2. Those multiply to 6, but if I add them together, I get positive 5. That doesn't work. How about negative 3 and negative 2? Let's check. Multiply those together in our mind. Positive 6. Add them together. Negative 5. Perfect. Done. Next, factor this trinomial here. The coefficient is not 1, so it would be nice if we can factor it out, which we can. The GCF for this trinomial is 3. So that leaves an x squared plus 11x plus 30. Remember, the 3 has to be divided out of all these terms. This trinomial here, I can tell just by looking at it that it's factorable. Well, this 3 is still there. Don't drop it. Okay. So we want to find two numbers that multiply to 30 and add to 11. Well, numbers that multiply to 30, how about 3 and 10? Well, that works, but if you add those together, we would get 13. So that doesn't work. We want 11. How about 5 and 6? 5 times 6 is 30. 5 plus 6 is 11. Perfect. Done. This next one looks a little bit frightening, but let's check. Can we factor out anything? Yes. The GCF is 5. So that leaves x squared minus 1x, or just minus x, minus 90. Okay. Well, let's hope that this is factorable, and I believe it is. So let's leave the 5 there. Let's set up the product of binomials. I'll put the x's in. Right. So we want to find two numbers that multiply to negative 90 but add to negative 1. Right. Well, I know that 10 times 9 is 90, but I need negative 90. So how about 10 and negative 9? Okay, well, those multiply, but if I add these together, I would get a positive 1, which is not what I want. So let's try it the other way. Let's try negative 10, positive 9. Again, those multiply to negative 90, but if you add them together, you do get negative 1. So those are the numbers that I'm looking for. Perfect. That one's done. Now I've just drawn a line here to separate what I've done from what I'm about to do, and that is I'm just going to show the check. Okay. Eventually, once you get comfortable with these, you don't need to multiply them back out to check to see if they're right. You just know that they are. Okay. But just for the time being, just as a good exercise, I will show the check. If you want to skip ahead and ignore this part, please feel free. So all I'm going to do is FOIL everything out, keeping in mind, though, that there's still a 2 in front of here, so we don't want to drop it. Okay. So I'm going to FOIL. So I get first, outside, inside, last. So I'm going to combine the like terms of what's in the middle. And now I'm going to apply distributive law, as you were taught in the beginning. Multiply everything by 2. Okay. And that matches what was originally given. So we know that this answer here was correct. Multiplying these, so the 3 is still there. Going to FOIL out these two binomials, so it gives me x squared plus 6x plus 5x plus 30. Combine those like terms in the middle. Again, do not drop that 3. It's still there. I need it so that I can multiply it back out using distributive law. Check that it matches. Sure does. And this one. So, foiling. Whoops, forgot the square here. X squared. And distributive law. Okay. Remember, 5 times 9 is 45, so 5 times 90 is 450. Just watch your signs. Okay, let's try this. Unfortunately, we have an x cubed. Now, that might be a problem, but it turns out it's not, because not only can I factor out the 2 as part of the GCF, I can actually factor out an x. The GCF is 2x. Okay, so factoring that out leaves x squared minus 12x plus 35. Okay, so pulling out that GCF makes this remaining trinomial a lot less frightening. Okay, so we need two numbers that multiply to positive 35 but add to negative 12. Okay, well that tells me that both my numbers must be negative. So this would be x minus 7, x minus 5. Because negative 7 and negative 5 multiplies to positive 35. When added together, I get negative 12. I'm not going to show the check. This is good enough. Next one. I know I can factor out a 5, but I can also factor out an x squared. So the GCF is 5x squared, which leaves x squared minus x minus 20. Okay? Remember, if you don't factor out this correctly, you're not going to be able to complete this trinomial. So we want two numbers that multiply to negative 20, but add to negative 1. I don't think that's too difficult to find. Okay, so one has to be positive, one has to be negative. Okay, let's check. Is it 5 and negative 4? Well, that works for the minus 20, but if you add these together, you get a positive 1. So these signs need to be fixed. Minus, plus. Perfect. Next. The next one looks really scary, but let's just look for a GCF. Well, for the numbers, I can factor out a 2. Look at the x's, I can factor out an x. And all three terms contain a y to the 5th. So that means I can factor that out too. So the GCF is quite large, actually. I'm just going to write it here. Just need more room. So 2x y to the 5th, which leaves x squared plus 11x plus, and that would be 28. And there we go. Well, suddenly this trinomial here doesn't look very scary at all. So two numbers that multiply to positive 28 but add to 11. That's easy. That would be 7 and 4, or 4 and 7, doesn't matter, they're both positive. 7 times 4, 28, 7 plus 4, 11. This one was easy. Next, negative 2x squared minus 10x minus 12. I have a little asterisk here, and that's because notice that the number in front of the x squared, not only is it not 1, but it's also negative. When that happens, a good idea is to factor out the negative as well. All right, so 2, 10, 12. Of course I can factor out the 2, but I'm going to factor out a negative 2. Because that means that this remaining x squared that goes inside here is positive. And that's what we want. It's just easier that way. But remember, when you're dividing out a negative, all of these signs have to change. So this would become a plus 5x, and this would become plus 6. Okay? And you can multiply this back out to check to see if you're right. Okay? Can we factor that trinomial? Yes, we can. Very easily, in fact. Two numbers that multiply to 6 and add to 5. Positive 2 and positive 3. Simple. Not too bad. The next example, looking for the GCF, I can factor out an x, and the number in front of here, well, it's negative 1. But again, because it's negative, we want to factor that out. So I'm going to factor out a negative x. Again, why do I factor out the negative? It's so that the x squared that goes inside is positive. So this becomes negative 7x, and this would become positive 12. And there we go. Can we factor this? I think so. Okay, numbers that multiply to 12, positive 12, but add to negative 7. Well, 3 and 4 would work, but when you add those together, that gives positive 7. So if this is negative, I want negative 4, negative 3. And that's it. We're done. And lastly, look for a GCF. I can factor out an x, which leaves x squared plus 7x plus 1. Okay, and now we want to factor that trinomial. Okay, so we need to find numbers that multiply to 1 but add to 7. I don't think that's possible. Well, the only numbers that would multiply to positive 1 that are whole numbers are 1 times 1, which adds to 2, or negative 1 times negative 1, which would add to negative 2. So it turns out there aren't two magic numbers that work. So we actually can't really do anything. So we write not factorable. It was partially factorable in that I was at least able to factor out an x, but I can't go any further. I cannot take this trinomial and break it down into a product of two binomials. Can't do it. So if I gave you this to factor, this is as far as you can go.